Hello everyone, welcome back to our low-temperature thermochronology online lectures. Today, we'll be continuing learning Chapter 9, Thermal History Reconstruction of Sedimentary Basins. I'm Nitao from the School of Earth Science and Resources, Chang University. This is the outline of this chapter, and we'll be learning the last section, which is the case study from South China. This very beautiful figure is a digital elevation map. We can see that the location of South China in the present day is along the West Pacific margin. South China in the Mesozoic was evolving to a giant granitic province that is in close relation with the eventual large-scale mineralization in this region. There are some key observations of South China during the Mesozoic worth our attention, including, first, an origin migrate towards the inland from 250 to 200 million years ago. 2. According to the basin records of South China during the Mesozoic, it is indicated that an origin and its associated foreland basin was migrating towards the Craton inland. And 3. Significant vertical movements, as is indicated by the topographic changes, is observed in this area. This is the paleogeography reconstruction map of the South China area. We can see that during the earliest time of Permian, about 285 million years ago, this area received large-scale carbon deposition. And if we consider this topography level as the reference level, by Middle Triassic, about 230 million years ago, the whole area was uplifted, becoming an origin instead. However, by the time of early Jurassic, about 190 million years ago, this area was subsidized and receive sedimentation again. According to this paleogeography reconstruction map, it is indicated that this area is becoming a shallow marine basin during the early Jurassic. Interestingly, this subsidence did not last long. By mid-Jurassic, all this lower Jurassic deposition had been more or less exhumed, and in Middle Jurassic, this area was dominated by magmatic events. According to the above observations, we can conclude that the South China experienced significant topographic changes from latest Permian to Middle Jurassic. And the above topographic changes and observations is well explained by a proposed tectonic model. In this flex subduction model, it is proposed that the orogenic front has migrated for more than 1,000 kilometers towards the cratonic interior during the time of early Mesozoic. And it is because of this orogenic migration that the whole area of South China was uplifted during this tectonic process. The deposition during the early Jurassic and the eventual formation of the shallow marine basins is explained in this tectonic model that it is due to the slab pool creating a second origin and a sag basin during the time of 235 to 180 million years. And during this time, a maximum depositional depth of more than 2 kilometers below sea level is expected. The Middle Jurassic exhumation and magmatic events are interpreted in this tectonic model by slab delamination and foundering, which created large-scale anorogenic magmatism and lithospheric rebounding. Inspiring by the proposed model and in order to test it, a southeast-northwest sampling profile was designed and samples were collected along this profile. The collected samples are lower Mesozoic sandstones and Paleozoic to Mesozoic granites. and a series of low-temperature thermochronology analyses are conducted, including zircon and apatite uranium thorium helium dating, zircon and apatite fission track analysis, and other geochronological dating methods, including argon-argon dating and shrimp uranium lead dating. Besides, cold samples are also collected along this profile to gather the vitronite reflectance data. The acquired data are shown in this table. In this table, we have the strata sequence listed here and the granite samples listed besides it. All the mirrored age data are listed here with the 2 sigma arrow-coded. To analyze the low-temperature thermochronological data in detail, the fission track data, including apatite fission track and zircon fission track age data, and apatite fission track length data are displayed in these commonly adopted figures. We can see that the dPAR of the collected samples ranged from 1.6 plus minus 0.2 microns to 3.3 plus minus 0.7 microns. This is an indication of compositional variation of the collected samples. The above data are comprehensively analyzed by 2 approaches. First, as is shown in these figures, is the inverse modeling using Hefty program, and second, the forward modeling by plotting the low-temperature thermochronological ages versus its closure temperature. You can see first from this modeling result that all the modeled age data or apatite fission track length data are listed here, and we can see the GOF parameter here as an indication of the agreement between the modeled and the mirrored data. From this modeling, we can see this heating and cooling event well defined by the inverse modeling using Hefty program, whereas in this forward modeling by using thermochronological age and its corresponding closure temperature, we can see that it also gives us some ideas of possibly heating and cooling scenarios. So how to combine this forward modeling and the inverse modeling? What we can do is that we can overlapping the forward modeling results and the inverse modeling temperature histories, as is shown in this figure here. The same, all these data are plotted using their low-temperature thermochronological ages versus their closure temperatures, and the thermal modeling path, which essentially is the inverse modeling path, are overlapped with these dots. So we can see that our inverse modeling and forward modeling results are in quite good agreement, that we now have the time temperature history of this studied area. And the next step is to see whether the tectonic model could fit with your thermal modeling result. So we can see that in this study, the tectonic model step-by-step correlates with the modeling of the history. For instance, during the Middle Jurassic to the Late Jurassic, this area is subjected to large-scale magmatic event, which should be corresponding to a heating stage. And if we go back to our modeling result in this time, we can see that, great, in our modeling result, there is an elevation in temperature, means that there is possibly a heating process. This is how our tectonic model fit into our time temperature history reconstructions. To sum up, this case study in South China shows us how to conduct a low-temperature thermochronology analysis and inverse and forward time temperature thermal history modeling use this acquired data, and how to relate our time temperature thermal history with the proposed tectonic model. The above is all for this section. Thank you for your attention.